Dear students, in this lecture, we will discuss about conduction of heat transfer through plane wall as well as composite wall. So, in the conduction heat transfer, heat is conducted. Means we use the mode of heat transfer, which is the conduction, in which there is the heat transfer from molecule to molecule, and molecule doesn't move. So, uh, there is the transfer of heat between two bodies or maybe between the two parts of the same body through molecules which are more or less stationary. Normally molecules are stationary because we are having their fixed position, and the solids are mainly the examples in which the heat transfer occur by the conduction. In case of the fluids or the liquids, the heat transfer mode is predominantly it is the conduction. For the conduction, we use the solids for the heat transfer. Now, for the heat conduction, we follow the Fourier's law. And this law states that the rate of heat flux is linearly proportional to the temperature gradient. This is the statement of the Fourier's law. So, it says that the heat conduction states the rate of heat flux. Heat flux means heat flow per unit area. This is written as heat flow. If we write as Q in per unit area, or so we could write Q upon A. This is the heat flux. It is linearly proportional to the temperature gradient. So for the single dimension, let's see here, Q is the heat flux. Q dot is proportional to dT by dx. So dT by dx is the temperature gradient with respect to length L. Now, here, because we are seeing that in this equation, this Q dot, which is the heat flux, and this heat flux is equal to minus K dt by dx. Minus K dt by dx is here. Where K is a constant of proportionality, and which is the property of the material, which is called as the thermal conductivity. Here the negative sign, which you can see here, this is the negative sign, and this negative sign indicates that this slope dt by dx is a negative. Actually, what happens when the heat flow will occur? Suppose heat flow is occurring from a temperature T1 to temperature T2. So here in this case, this is the heat transfer occurring. So always it is possible only when the T1 is greater than T2. If we find the temperature difference dt, then this dt will be equal to T2 minus T1. Because here T2 is less than T1, so this will give you the negative. It means the heat flow occurs only when there is negative temperature gradient, or the heat flows always in the direction of decreasing temperature. So the negative sign comes here because of this reason. Now to find the value of rate of heat transfer, we have to integrate the equation. So for this equation, we can write minus q by k dx dt. And here, if A is the surface area normal to the heat transfer, then total heat transfer is written as this. Q is equal to QIA. This is the heat transfer area. So this Q minus Q by K dx equal to dt. And by integrating this, we have to integrate this. Then by integrating this, we can get this dt will become T2 minus T1. And this is Q by K. Within the 1 to 2, it is 1 upon a dx. Now we see here for a finite temperature difference across a wall having thickness x and constant surface area A. For a finite temperature difference across a wall which is having a thickness x and constant surface area A, we can write T2 minus T1 equal to Qi minus K dx or minus Qi K x. So by using this, we can write the expression of heat transfer Q equal to K T1 minus T2 by x watts. So this is the expression for heat transfer through a plane wall across a finite temperature difference. So y is expression, we can calculate the heat flow rate. Now here x we have taken the thickness through which, so it depends upon x. If the x and q both are reciprocal, so if x increases then k decreases, and if x decreases then k increases. So these are reciprocal. It means if there is a wall of the larger thickness, if the wall is having the larger thickness, this is x, suppose its thickness is x1, and if there is a wall of the smaller thickness, that it is having thickness x2. Here definitely x1 is greater than x2. And what will happen in this case? Because x is reciprocal to q, if the x will larger, q will be lesser. Means the heat conduction through a thin plate will be more, but heat conduction through a thicker plate will be less. Now next we can see the analogy between the heat transfer rate as well as the heat flow rate as well as electric resistance. So we can very simply see here, according to Ohm's law, as we know that I equal to E by R or IVR, as right, I, which is the flow of the current, equal to V by R. V is the potential difference or voltage upon R. So the current flow depends upon the potential difference as well as resistance. Similarly, in case of the heat conduction also, this can be written as heat flow rate Q is equal to delta T, which is the temperature difference, divided by RT as thermal resistance. This heat flow depends upon the temperature difference. If the larger temperature difference are there will be more and more heat transfer. But it is reciprocal to thermal resistance. If the thermal resistance is higher, heat flow rate will be lesser. If the thermal resistance is lesser, heat flow rate will be higher. So we can see here, this is a some plate, and it is having two surfaces, and the heat flow is occurring along this direction. The heat flow rate. Suppose it is the stationary conduction. In that case, the temperature on two surfaces here at this point, temperature is T1, and at this point, temperature is T2. So definitely, temperature T1 is greater than temperature T2. The heat flow will occur, and the direction of heat flow is perpendicular to this area. You can see this area, and the heat flow is occurring perpendicular to this area. So in the conduction, the area which is considered, it is perpendicular to the direction of the heat flow. So heat flow is occurring here. Now this is written here in terms of that resistance. Q equal to K T1 minus T2 by X. This is in the watts. Then we can write Q equal to T1 minus T2 by X by K watts. So this T1 minus T2, which is the temperature difference, divided by X by K. Here X by K, this indicates the thermal resistance. This is the thermal resistance here. Here written here RT. So RT is what? It is the XT by K thermal resistance. So temperature difference upon thermal resistance is the heat flow rate. This is the thermal resistance. Now we can take the example of a composite wall. So what is a composite wall? A composite wall is nothing but it is a wall composed of more than one wall, and they may be of the different material. So here you will see the heat flow rate is occurring perpendicular to this plane. At this point, the temperature is T1. It's the maximum temperature actually. This is the first plate which is having thermal conductivity K1, and second plate having thermal conductivity K2. It means they are made of different materials. So because of that, thermal conductivity are different. At this surface, temperature is T2. You can also take temperature T2 here and T3 here. This can also be done. The heat flow will occur. Now, how this is represented using this Fourier equation? So, in this case, we are seeing there are two thicknesses. They are thicknesses. For the plate 1, thickness is x1. For plate 2, thickness is x2. We will take. So, for the first plate, thermal resistance will be R1. For the second plate, thermal resistance is R2. It is x1 by k1 for the first plate and x2 by k2 for the second plate. Then what is the heat flow rate? It is the total temperature difference upon total or overall thermal resistance. So T1 minus T2 upon x1 by k1A plus x2 by k2A. The resistance are directly here added in series. And using this relation, we can find the heat flow rate for this composite wall that we can calculate. Here K1 and K2 are the thermal conductivity of the different plates, and X1 and X2 are their thicknesses. Now there is possibility that the heat is flowing or conducting through the composite wall or maybe a plain wall but having the different areas. Here the calculation of the thermal resistance will be different. How it will be? Just see here. Heat flow rate occurring is Q. Here also Q. So it is the steady state. But the this plate is made of two portions. Upper portion you can see having some material having thermal conductivity K1, and the lower portion is having thermal conductivity K2. So this actually these are made of some. This is the separation line. You can see this is separation line. I of this line, the material is different, and below this line, the material is different, having thermal conductivity as K1 and K2. But the temperature is same. At this point, temperature is T1. Here also temperature T1 on the left hand side surface. On the right hand side surface, you will see here at this point temperature is T2. Here at this point temperature T2. So on the two faces, temperatures are different, but areas will be different. At this point, the for the upper portion, the area is A1, and for the lower portion, area is A2. So in this case, the heat will flow, but the resistance will be separately calculated for this portion and this portion, and they will not be added directly because this will be the case of the parallel. So how it is calculated, how it is taken, just see here. Here you will see the total resistance. This is 1 upon RTH equal to 1 upon R1 plus 1 upon R. It is taken in this way. So for the first plate, it is K1 even by X1. For the second plate, it is K2 A2 by X2. And using this relation, we can write this is the overall thermal resistance. And using this relation, we can calculate the thermal resistance for this plate having the different materials as well as different uh, surface area. This is the way how we can calculate the thermal resistances as well as heat flow rate of the plane wall as well as composite wall which are in series having the different materials, and the plates are having maybe in parallel with different materials. How we can calculate.